I'm Jolie Boyer, and this is Physics 2212 Lab 5, Magnetic Braking with Faraday. The purpose of this lab is to observe a magnet falling through an aluminum foil tube, and then we simulate this motion in a computational model and compare the model and the experimentation to further our understanding of Faraday's law. On this slide, I've also listed the findings that we will discuss later in the lab. The physics principles needed for this lab are Faraday's law, with which I've also listed the formula to find the magnetic flux. We also need to know the formula for magnetic force on a wire and Ohm's law, and we also need to keep in mind Newton's second and third laws. The assumptions for this lab are that air resistance acting on the magnet is completely negligible, and in hand with this, we say that the only forces acting on the magnet are the magnetic force of the aluminum tube and gravity, and the system in this experiment are the magnetic foil, the magnet and the foil, and the surroundings are everything else. The procedure we followed for this experiment was to mark the magnetic north of the magnet, measure the constants. Then we took 5 trials and dropped the magnet through the aluminum foil tube and recorded the time of each fall through the tube. We then modeled this interaction in GlowScript, and we compared our observed and simulated data. Our experimental data is recorded on the slide. One thing I would like to point out is that we are using mu of the magnet from lab 3, which I found to be 2.57 amp meter squared. And then also on this slide we have this table in which I recorded the trials and the time for each trial, and then at the bottom you see the average that the magnet fell for 1.29 seconds, and here is also a clip of one of these trials. Included in the experimentation part of this lab were some checkpoint questions, which are, why can't we use a ferrous tube? This would skew our data in this lab because of the magnetic properties of iron that is present in ferrous tubes. And what is happening to the magnet? How does this compare to a magnet falling in free space without a tube? A magnet falls slower in the tube than it would in free space because of an upward magnetic field that is created due to the induced current running through the aluminum foil due to the dipole magnet. I then moved on to the computational modeling. The first step of this was to input mostly just the constants from our experiment, what we found the magnet and tube to be, and also just gravitational constant and things such as that. And then there are portions from the starter code included that I didn't actually have to edit here. And then the next part that I had to do was to calculate the dipole from the magnet. So using mu and r we found, and the equation for a magnetic field, we found the magnetic field exerted on the tube by the magnet. Moving on, we then calculated the flux from that magnetic field and found the current moving through the ring of the tube, and then expanding upon this ring, we essentially iterated it for the entire length of the tube, and then we found the magnetic field exerted on the magnet from the induced current in the tube, and then we solved for the net force, and using Newton's second law at the very end, we updated the bar velocity and the magnet position. Okay, these are the results of our lab. At first we ran with mu from lab 3, which was 2.57 amp meter squares, and then we found the time in the tube to be 0.66 seconds, and the graph looked like this. And then in the second part we tried to find a mu that would match the experimental time, and that mu that got 1.29 seconds was 3.6 amp meters squared. As for discussion of our results, let's first go over possible sources of error. There is obviously human error during experimentation. Potential improper calculations of mu in lab 3 could have affected our initial results in this lab, and also the other forces that we neglected can have effect on the fall of the magnet. As for further discussion, what if the resistivity of the conductor were reduced to as close as possible to 0? This would reduce the resistance within the foil and would create a much larger induced current and larger magnetic field, and the magnet would fall even more slowly through the tube. And what if holes or slots were cut into the tube? How would this affect the ring currents in your model? Holes or slots would disrupt these ring currents through the foil and would decrease the induced current and magnetic field, and this would result in the magnet falling faster through the tube than seen in the experiment. Thank you.